Swayam Prabha. Digital India. Educated India.
Okay, good morning. Welcome everyone to day 4. I think one of the most exciting day part of this course because we'll be going through a lot of deep learning things. So all the models that techniques, models that Kamal will be talking today, these are really at the forefront of what is happening in this entire domain of materials informatics. So like we talked about different benchmarking, right? So all the model architectures that Kamal will be discussing today, these are the leaders in these benchmarks. So far, what you have covered is just getting started with different types of doing materials computation, then the basics of AI ML, and today you'll be seeing what are the most best performing models in this area. Okay, and then tomorrow will be the last day where we'll look at some other way of using these methods to actually guide experiments. Okay, yeah, Kamal, over to you.
Thank you, Rohit. So just want to point out, it really took a lot of effort for Rohit for arranging this, inviting me here. He has done really a lot of work. Can we give him a round of applause, please? Thank you, Rohit. All right. So getting started on the 4th day. So if you thought we learned a lot in last 3 days, so it's not even the tip of the iceberg. So now we are going really into this thing on materials informatics. So we learned, we discussed, we yelled at each other a lot for last few days on very basics of materials informatics, density functional theory, molecular dynamics, feature-based machine learning, and so on. But now we are going to go in a different field, a very exciting field on deep learning. So we discuss all of that. And by the way, all the slides are now also in the GitHub repository that I sent it to you. I think in PDF format, so feel free to download. All right, so day 4th, we have a lot of things to cover, and I'm told that I can take 30 minutes extra today compared to yesterday. So today we'll talk about CNN, convolutional neural network, GAN, generative adversarial network, graph neural network, generative pre-trained transformers, too much mouthful, Atom Vision project, Align project, Chem NLP project, Atom GPT, Diffract GPT, and Leaderboard. So too many things to cover, but we'll go slow. We'll pause whenever we transition from one to other project. So the first one I want to start with is Atom Vision. So last few decades, we have seen a lot of development in the field of computer vision, right? So the idea of Atom Vision is modeling atomistic images or analyzing atomistic images, which is available at US NIST/Atom Vision. Now, there are certain features or certain capabilities of this particular module or package. First, it can be used to generate DFT, density functional theory based image data sets. So remember, the first thing is getting good data set. Second, it can also be used to obtain experimental image data set from literature like arXiv or so on. It can be used to for NLP based image data set as well. So experiment and NLP based image data set. It can be used for classification, such as cat versus dog, but in terms of material science, Bravais lattice, like cubic system, hexagonal system, image segmentation, so an object detection, such as not just saying whether cat or dog, but where the cat's ears are or eyes are. So that kind of information. And also it can be used for making graphs. So these are some of the architectures or some of the methods that is used in Atom Vision. So first one, for example, is we talked about convolutional neural network, right, yesterday. Remember blocks of patches of convolution filters. DenseNet is a kind of a much enlarged form of this. So you have multiple such layers on DenseNet. UNet is also another architecture which is used for. So the DenseNet is used for global classification, global prediction, UNet for pixel-wise classification. Autoencoder we discussed, and something we did not discuss yesterday is SRGAN, so super resolution GAN, which kind of some people call it the cop and the thief game. So you have a generator and a discriminator. So generator try to generate new images, and discriminator try to falsify it. And there's a competition who wins, and whoever wins, the image is generated based on this. So we'll discuss a little bit about this as well. So first, and probably most important part, how to get good data set for images. So we are going to use something called scanning tunneling microscopy images. So you can do STM image experimentally, but it's very time consuming. And you can do it on 2D materials, 3D materials, and so on. So how many of you know about 2D materials? Please raise your hand. Okay, so let me briefly talk about this. So there are different classes of bondings, right? So we talked about this in the previous slides: chemical bonding, van der Waals bonding. So when there is a van der Waals bonding in one direction, right, that is called 2D material. When van der Waals bonding in two direction, that's called 1D material, and van der Waals bonding in all directions, that's called 0D materials. Okay, so we will be focusing mainly for the image data sets to be 2D materials. Why? Because when you have van der Waals bonding in your 2D material, the chances of surface construction and the dangling bonds when you cut the surface is very low. So that makes things more realistic in terms of comparison to experiments. So in a nutshell, if you completely forget what I said in last 30 seconds, I'm going to try to make the images as realistic as possible, and for this we're going to take 2D images, 2D material images. So one of the approach for scanning tunneling microscopy is based on Tursup-Hammond approach. So we learned about the density functional theory and charge density. Now we can assume the theorem proposed by Tursup-Hammond is the intensity of scanning tunneling microscopy is proportional to the density of states. Okay, that's the basic assumption, and based on this assumption, which is basically saying tunneling current is proportional to integrated local density of states, and based on this we can probe where atoms are and where it is not, and based on this you can get tunneling images. So on the left hand side we have theoretical images for graphene, I think MOS2 and iron telluride, and on the right hand side we have the experimental images. As you can see, these are comparatively very close to each other. So the idea is if you can do machine learning on synthetic or DFT based images, the same can be applied if we have enough amount of experimental data. And then we have similar example: black phosphorus, I think molysulfide and tungsten telluride. So it compares well, and we have a data set published in Nature Scientific Data a few years ago. Similar to the STM, there is another technique called STEM, scanning transmission electron microscopy. So where it can be modeled using something called Rutherford model. It's a very basic model in a way. It's saying that if you have if you have an atom like Z atomic number at position R, and then the intensity of that pixel is proportional to the atomic number square. That's all, nothing more than this. But 1.7 because you have some loss sometimes, so it's not complete too. So and this also can be very comparable to experiments, especially for 2D materials. For 3D, again, we have dangling bonds, this and that, so it's not that much comparable. And for that, you need something like multi-slice simulation and other, which takes into account phonon contribution and so on. But here we are dealing with a very cleaner case. So the first task for this is any image learning task is classification, this image classification. So we can classify any, remember we talked about 7 crystal lattice in 3D. In 2D there are only 5. Okay, can anybody guess how many in 1D? Anyways, yes, we can come to that later. It's a lot of fun because not just 3D, there are like 4D, 5D, 6D, 7D materials, and there are different kinds of crystallography in that. Maybe I won't have time, but it's a very fun topic if you want to learn about this. Anyway, so in 2D material there are 5 types of lattices, and you can see that this is the actual material, the visualization of this. This is the STM images, and what if you take Fourier transform of this, how would it look like? So very commonly people use Fourier transform of the images to classify a material, but it can also be much useful to use machine learning techniques, especially when you have lattices like parallelogram and rhombus where it's hard to detect, while in hexagonal and square it's relatively easy to figure out what kind of lattice it is. So again, we have generated this data set of, I think, 6,000 2D material images using STEM, and these are, I think, 256 by 256 images, 256 pixel by 256 pixel intensity images. So whatever that number is, 256 by 256, 62,000, whatever, 600,000. Now we can do the similar thing we did yesterday, like called T-SNE plot, remember, where we try to compress all the huge dimension to 2 dimension. If you do that and color code each data point based on the lattice system of the 5, this is how it looks like. So it shows you there is some sort of clustering possible. They try to, even in the pixel intensity, they try to cluster in a way. And this is for pixel, and also one of my postdoc, Ramya Gurunathan, she did some really fantastic work with visualization, and she did based on the bond angles and stuff, just T-SNE based on bond angles, which was also interesting. So this is again just EDA, exploratory data analysis. Once we have done this, we will try to do the classification. So we will have the neural network which will predict the classes 0 to 5, okay, and we will try to run one of the examples in the hands-on session with the actual data. So one of the way to visualize this performance of this model is called confusion matrix. So what is a confusion matrix? Where you have x and y axis by true label and a predicted label. So from 0 to 4 for 5 labels. If it's all 100% correct, so suppose you have training and test data set, and if it's hexagonal lattice and your model is also predicted to be hexagonal lattice or rectangle lattice or whatever, completely this will be 100%. But if it is hexagonal but it's predicting to be square, then there will be a contribution here and so on, off diagonal contribution. So that is how we build the confusion matrix. We can achieve up to, I think, 89% accurately classifying based on the images using DenseNet. Now the baseline, again, remember we talked about before doing any machine learning, do a baseline. So what will be the baseline of this classifier? Anybody can guess? You have 5 labels. 20%, yes. So assuming it's a so all of the images have similar distribution, the probability of getting them correct is 20%. But here we are getting about 89%, which is much better than baseline model. I'll not discuss about this, the second part, but you can also convert images into graph, where the image intensity will serve as a node, and the connection between them will be edges. So we can classify images like this too, and that gives you up to 83%. So seems like the graph neural network did not beat the CNN yet, but CNN still dominates. So this is the thing, unless you try it, you will never know what kind of model will work for a particular machine learning task. So this was global classification, okay? So when we have 5 type of lattice, sometimes what we need is the localization, not just classification but localization, pixel by pixel classification, or for detecting multiple images, or detecting where the eyes are, where the ears are, and so on. Or in terms of material science, we want to detect where the atoms are, where the vacancy is, and so on. So for this, we use something called semantic segmentation. So this is already also available in Atom Vision, but the idea is you have to give a data set where you know exactly what pixel is what. That is pretty difficult for experiments. So that's why the idea is we train the model on this this kind of data set which we generated from theory, and then once the model is trained, the model should be capable to be transferred for experimental images as well. Okay, so so we trained we first developed this STEM image data set, and because we developed it so in a very controlled way, we know exactly where atoms are, right? Because of the Rutherford intensity model. So we had a 256 by 256 pixel and 256 by 256 labels. That makes sense. So this 256 by 256 to other part of same dimension. So this is called UNet. So you first take this model, add another layer, completely have a bottleneck layer, then again sort of decode and go in a U format. This is called a UNet. And if you can establish this, you can detect atoms very accurately. UNet is probably one of the most popular semantic segmentation model in entire computer vision community. So very interesting. I think from some German group. So semantic segmentation, and you can see we can detect where the atoms are and so on, except some of the boundary atoms, where it gets confused sometimes. But it does reasonable job in terms of detecting atoms. We won't be running a hands-on session for this one, but there is scripts in the GitHub. We also talked about yesterday about autoencoder. So we take image data set and try to have a bottleneck layer and another generate an image from there. And then this latent feature or bottleneck feature, we try to vary from 64, 122, 1500, 3000, so on like this. And we saw what gives us minimum loss. So we can see that 1500 seems to be a good dimension for this 256 by 256 images. Just adding more latent feature actually can increase your loss or increase your error. So you always have to do this kind of comparative scaling. And again, if you have this model ready, then you can generate a 1500 random numbers and it will generate a new crystal structure for you. Okay, so this was CNN, okay, convolutional neural network or similar to image kind of data set. Okay, so the next model is graph neural networks. So we talked about yesterday as well what kind of non-Euclidean problems we can solve with graph. And there are different types of graph neural network for material science, for atomistic material science. For example, crystal graph convolutional neural network or CGCNN, Align, Magnet, ICGCNN, there are many such models. We will be primarily focusing on Align models, so which is available at this GitHub page. And I think the two key papers, there are like several papers on Align, but two key papers is, first one is for property prediction, given atomic structure, predictive property, or do a force field training, like run a molecular dynamics simulation or structure optimization with this for the entire periodic table. So did we discuss this graph yesterday? I forget. We did not, right? Okay. So the way we represent a graph, atoms is as a form of graph is, suppose you have blue and red atoms. So these are silicon and oxygen, so it's SiO4 tetrahedra. Now you can have something called nodes, which are basically atoms, and the edges, which are the bonds. So the nodes can be atomic number, boiling point. These are the features, a way to distinguish one atom from another. And then you can imagine, like, if you have different number of atoms in a crystal structure or material, the number of bonds will be different. Same with the number of atoms. So how do we make it a way it is uniform? Okay. So what we do in this case is we take the interatomic distances Rij, all of them, and we have some sort of origin where we want to start, and then we do some sort of histogram in a way. Okay. So with that kind of histogram, you can make a similar kind of feature, similar size feature, right? And do it for many origins, not just one origin. Okay. And you add, again, you multiply with a weight layer and bias term and stuff like this. So this is fine. And then what about angles? So calculating angles for larger cell becomes very tricky, very time consuming. So one of the ideas we proposed is this thing called line graph, where we can consider these edges as the bonds and the edge pairs as the new edges. Okay. So basically, instead of having Ij, we have Ij and Jk, and that will give you the angle contribution. Okay. Now, if you take the line graph of this bond angle graph, can you tell me what will happen? What can we do with this? If you take, so we took the line graph of this atomistic graph, we can calculate bond angle. What will happen if we take a line graph of this? Yes. So we took the nodes and edges and stuff. You can describe a graph, and in the line graph, we considered the edges as the bonds and the edge pairs as the new edges of the bond graph, angle graph, and we can calculate angles. Now from that angle graph, we take another line graph of this. Now what will we do with that? What is the advantage of doing that? So the triple, the third layer up. So we can get dihedral angles, if it makes sense. Now if you can go n number of ways, you can get n body interactions, right? But we stop at the angle. Okay. So with this kind of graph and line graph, you can predict properties at graph level, which is like total energy, total band gap, total, everything. Or you can have node level predictions like charges on atom, magnetic moment on atom, uh, what is called atomic density of states, atom projected density of states, uh, X-ray absorption spectra, I don't know, K edge, L edge, and stuff like this. Or you can have node level prediction in a way that it is derivative of the graph level predictions, such as forces. So just predicting forces is not enough. The energy needs to be conserved. So the forces must be a derivative of energy. So you can establish a relationship, and you can get forces. You can also have edge level predictions, like for each edges, give me tight banding parameter or Lennard-Jones parameter, and so on. So it's very versatile in a way, and the things we can do with this. So this is quite involved graph, but suppose these my 4 atoms, and for each of these atoms, we have the node features, atom features or node features, and then we throw it into a kind of embedding. What is embedding? In kind of way that it's like a histogram kind of thing in a way, right? To make it same shape, same dimension. Even the number of atoms in different materials could be different. And then we can do this the same for bond features and triplet features, and concatenate that number. Okay, and from the concatenated thing, you can predict like global property like energy, band gap, and whatnot. Or if you have the node level features, you can predict like charges, magnetic moment, or and so on. Okay, so it's very versatile methodology. Am I talking? Does it make sense what I'm saying, or yeah? Any questions? Okay. Okay, so one of the first thing we did is predicting the graph level property. So formation energy, band gap, and remember we talked about the baseline model. So the MAD here represents the baseline model. So the MAE, you can see for some of the properties 50, and for some it's like 1.49. So it shows that there are some properties of materials which is much easier to learn compared to others. Okay, so just because we have this angle doesn't mean we have solved the problem. There's still a lot of room for improvement. So for example, total energy is pretty good model, and this is probably one of the first model which actually showed this kind of unified nature of property predictions, because people have fit energy forces forever for last few years, but this was the first model that actually showed a diverse amount of properties can be fit with this kind of graph network model. So this was scalar property, right? But a material can also have vector or multidimensional property. So one of this multidimensional example is like phonon density of states, electron density of states, carbon dioxide capture, like in a grid or something, X-ray diffraction pattern. Here in this case, we wanted to design superconductors, Bardeen, Cooper, Schaefer superconductors. So they are conventional and non-conventional or unconventional superconductors. For conventional superconductors, there is a theory called BCS, and there have been several Nobel Prizes for this. So the idea is the highest temperature of BCS superconductor they have found is 39 Kelvin. Anybody know what material is that? It's MgB2, magnesium boride. Okay, that is the only material which has highest conventional high temperature superconductor. If by any chance somebody can make a room temperature superconductor, then we will never need battery ever. Imagine never charging your phone. Won't it be nice? But it's a very difficult problem. Why? Because they require the calculation of electron and phonon coupling, and it's very time consuming. So what we wanted to do is train a machine learning model that can predict this electron phonon coupling. And one of the way to represent this electron phonon coupling is called Elias-Berg function, alpha square f. Okay, so it's like phonon density of states, but it has electron description as well in a way. So we generated a material data sets in this paper, designing high TC superconductors, and then we again 90-10 split and so on, and predicted the Elias-Berg function as a multi-value property. And you can see for the test data set, even for the worst one, it gets reasonable shape. So it's not just learning, it's a table. So it's not like a database only. It can actually be used for a new material as well. So we actually use this model to screen several 8,000 or some superconductors, and actually validated 50 new superconductors which was never reported before. So this method can actually work. Now some of our experimental collaborators trying to make some of this, but honestly I don't think we have met room temperature superconductor yet. Okay, so but hopefully we can someday. All right, so another is similar multi-value property is carbon capture, or which is a carbon dioxide isotherm, adsorption isotherm. So for this, we use something called HMOF dataset, hypothetical metal organic framework dataset. So the metal organic framework is a kind of material which has, do you remember coordination complexes in chemistry? It's like that kind of compound where there is a metal ion, a transition metal ion, there's a lot of void, and in that void, carbon dioxide can be captured and released. That's the idea of MOF. There are MOF, there's COF, there are many types of materials like this. So luckily, this Northwestern University group developed this very nice HMOF dataset, and we just use, and they have multiple properties using a grand canonical Monte Carlo, which we did not discuss, but it can have surface area, pore diameter, carbon dioxide, and then as usual, using this graph neural network model, we did 80-10-10 split of this 137,000. I think it took like 3 days to train that model on GPU, and then we get very nice performance. But we also test this model on experimental structures, and you can see these are actually our own experiment for some new compound which was not in the training data set, and you see how this gravimetric surface capacity and CO2 at 2.5 bar compare with that experimental data pretty nicely. So to run this one of these experiments takes humongous amount of time and resources, but these kind of models again can be useful. All right. So so we did single value prediction like band gap, formation energy. Second was multi-value prediction like CO2 adsorption. Third is gradients, which is the forces. So we took this Jarvis DFT data set, which has about 75,000 materials. And if you are familiar with DFT, and we did talk about it, it takes several steps to go to the ground state energy minimum. So for each snapshot, it calculates energy and forces. And we suppose store all of that for 75,000 materials for each material. That leads to 4 million entries, 4 million energy and forces pairs. Now we can throw all of that information in graph neural network to have a really good model, right, to predict energy and forces. But at that time, and even now, we don't have the GPU capability to train 4 million entries. So we had to downsample how much material we'll train. So we took the first, last, middle, max, and min step only, instead of taking entire trajectory of SCF run, and that gives you 300,000. So that is reasonable in terms of training. So we trained the energy and forces, and you can see again straight scatter plot is what we want to see. And also want to point out the loss function we discussed. So in the loss function, we had different weights for the forces. So we have weight for 0.1 up to 10, and you can see if you have 0.1, your forces error is high, but if you have high weight, then the MAE errors are low. So it depends what kind of problem you want to solve. If you have a problem which requires more accurate forces, then you want to use this model. But if you have a problem which requires more important energy, then you use this model. Okay, and there are some examples that we'll try to go through as well during our hands-on to develop a regression model, which is like property prediction as well as machine learning force field model training. And this model, once trained, can be used for any combination of materials to predict their equilibrium structures. Like silicon, for example, has I think lattice constant of around 5 angstrom, I forget. So suppose you give 8 angstrom, and suppose you did not know the lattice constant of silicon, then what will you do? So you'll put some structure like diamond structure, give 8 angstrom as a lattice parameter, and throw in this kind of model, and it will bring it back to 5 angstrom. So these are one of the applications of this. So another way to validate this is it can capture different chemistry. So for example, it's kind of alloy, multi-component alloy, and although we did not train for energy volume curves like compression, expansion, it can also predict those kind of behavior pretty accurately. So which is also a way to show like this kind of models are not just good for interpolation, but to a certain extent extrapolation. Excuse me. And then not just chemistry, but even for same chemistry, you can have multiple prototypes like silicon in diamond structure, cubic structure, monoclinic structure, nickel, aluminum in L1-2 structure, and so on, like how we arrange atoms. And it can distinguish or it can differentiate the energy difference between those two, which are important. And again, these are all the good things. There are a lot of bad things as well about this model, so which we can find in the paper or some of the notebooks we have. So this is an example how we can run actual molecular dynamic simulation of making aluminum oxide, amorphous aluminum oxide. So in many technological or semiconductor application, we are interested in amorphous materials. Okay, so we can, if you want to take a material and melt it to 5,000 Kelvin, relax it suddenly, then it becomes amorphous. Now, if you want to do this using DFT, it will take a lot of time. For force field, classical force field, there may or may not be a good force field available, and it might be also time consuming. So that's where this kind of model may be useful, where you want to quickly run MD simulation and stuff. So ours is not the only model like graph neural network, and really any major company you can think of has jumped into this area. There's a model for this universal force field by Meta or Facebook, from Google, from Microsoft, I think from IBM as well. So all of these companies have this model. So our team decided to work on a project to compare them in a neutral way, which one is better for different properties. So we considered these 14 or 13 models. So AlignFF, ChargeNet, MACE, MATGL, 7net, Orb, MatterSim, and so on. These are some of the models. And the properties we are interested in, the error in lattice parameter of semiconductor models for, I think, 100 semiconductors, because we wanted to decide, we wanted to focus on chips material or semiconductor materials. So we wanted to calculate error in error A, B, C, bulk modulus, phonons, and how much time does it take to calculate that. And we also compared the amorphous behavior, which can give more accurate amorphous radial distribution function compared to DFT. And it's a lot of interest is there right now. In we put this on, I think, LinkedIn and Twitter, and almost all the people who work on this started, sharing, liking, commenting. So far, no bad comments, so which is good. So, but there is a lot of interest in this kind of benchmarking force field, because usually what people do is energies. They just compare energy and just call it a day. But as a material science or material science engineer or a scientist, we want to also calculate like phonons, thermal conductivity, thermal expansion, and all this kind of behavior. So this chips FF is also a GitHub repository that lets you kind of use this as a Lego, or just add and break kind of thing, and predict different properties. So now we talked about scalar property prediction. We talked about vector or multi-value property prediction. We talked about force field. Now we'll take it the reverse way. So what is the reverse way? From the day one, I have been emphasizing on processing, structure, property, performance relationship. Now we'll think about the other way. Performance, I always forget. Performance. No, not structure. Performance, property, structure, processing. Yes, I should give a test to kids. Tongue twister. So we want to go the other way. We want to give from property to structure. And it's similar to the idea of making an image. Like you go to ChatGPT or DALL-E and write, make me an image with a bear with a guitar. Okay. Now what will happen is, you can see this generates the image. Wouldn't it be nice if you can do this for crystal structure? I want this property generated with the crystal structure. Okay. So that is the goal of any material scientist, right? So there are many models for this, and one of them we use for superconductor design is called CDVAE plus align model, or crystal diffusion variation autoencoder. So just 2 days ago or 3 days ago, there was a model from Microsoft called MatterGen, which is kind of the successor of the CDVAE model, and they're also very popular right now. Anyways, so what happens here? Remember we talked about, you took a crystal structure, we took the node embedding, edge embedding, angle embedding, concatenate that in one hidden feature, latent feature. Consider this layer as that latent feature. Okay. Now, usually what we do, we take this and predict forces or energies or, I don't know, band gap or whatever. But what these people did, they wrote a neural network that can predict first the number of atoms in the system. What will be the number of atoms in a given structure? Once you have that, what should be the atom types? So suppose you have this model randomly predicts 8, and then we have to predict 8 atomic number. Now we have to predict 8 XYZ coordinates, and we have to predict 3 by 3 matrix for the unit cell. So you have 3 kind of things: atom types, lattice vectors, and what else? Which one? Atomic number and coordinates. Coordinates, yeah. So, and we don't do this in a one single way, but do again diffusion way. Remember, we talk about diffusion process. We take a model, add the noise, then denoise, and then this model was quite successful in generating superconductors. We took the Jarvis superconductor data set and generated 3,000 new superconductors. And based on the model we developed in the previous slides on the predicting the transition temperature, we have multiple filter. I want high temperature, low formation energy, and low band gap. Okay, because insulator cannot be BCS superconductors. So, and then we verified further with something called Macmillan-Allen-Dyne formula using density functional theory, and we discovered some new thermodynamically and dynamically stable superconductors. So, which is published in Journal of Physical Chemistry letter by my postdoc Daniel Wines. Did fantastic work. So, this is fine. This can also be used for designing interfaces. So, which is a project called Intermat. So, all these projects that I showed you earlier are dealing with perfect materials in a way, but all the devices are interfaces, multi-layer interfaces. So, the first thing I want to know how to, if you have a two set of material, how to put them together. Okay. So, if you put them together, it's like there is an algorithm called Zohr algorithm. I won't discuss about this, but I think we did discuss about this maybe, yes. So, first we get the smallest possible lattice from each of them, put them together, but even if you have two together, you can have translationally, you can just vary it in x and y, and you don't know where sometimes the atoms are on top of each other, and sometimes when atoms are top of each other, there will be high energy, right? We want somewhere in the equilibrium position, and usually people use DFT to find this energy, right? But here we use align, and it's much faster. So, if you want to generate crystal structures for interfaces, where there's two interfaces, 5 interfaces, it's very useful. And we also trained a model to predict the band alignment, the CBM and VBM, valence band maximum and conduction band minimum. So, using align model, and that we proved that although we trained that model on bulk materials, it can be used for surfaces, which has never seen before. And once you have that, you can have, for example, if you take silicon on top of silicon carbide, how will the band look like, conduction band and valence band, and based on this, the electrons will flow, and then you can decide whether it will be like, photodiode or transistor or something like this. So, it's very useful. Using this model, we characterize 1.3 trillion interfaces. This is highest ever reported in any material science literature. 1.3 trillion. How did we get this? Suppose you have 10 materials, the number of interfaces you can make is 10 C2, right? Suppose you have how many 100,000 materials. You can imagine how many numbers you can compute. Really huge, and this is just binary. You can do ternary, quaternary, and stuff like this. Is a huge material space in terms of interfaces. And if you want to compute DFT-based band edges, it's like almost impossible. Even with the machine learning model, it took 15 days to calculate 1.3 trillion materials. 15 days, because you can have maybe for each material you can do 1 second, right? 1 or 2 seconds. So for 1.3, you can do the math. How many seconds would it take? Okay. So that was interface design. We can use this for defect material design as well. So you have a perfect material, you take one atom out, okay, and then you calculate the energy, and then you have chemical potential of that element. And if you subtract this defect and energy level minus perfect plus the chemical potential, this thing is called defect formation energy, or the energy expense to take an atom out from a material. And we saw very interesting. All right, so defect wise, what we did is we trained the model only on perfect materials again. There is no defect in the system. Now we pop out few atoms and calculate energy, and you can see it's not exactly the straight line we are looking for, but it's not pretty bad, not bad in a way. It's the first attempt, right? There is no training on any defects. And there is another model which did they generated more and more defect data set, actual defect formation energy, and trained the model for different charges on atoms. So defects can be have charges as well, So they saw that this model can work for that as well. So there's also this project called defect mat. So in material science, there are a lot of defect and interface problems, and it shows that this kind of models can be useful for this one of the most challenging parts of material science. Question?
So all these, like when you're calculating the defect formation energy, there are different parts, right? So are you calculating the energy of all these parts using Li?
Yes.
And then you are just putting it in the formula and
Yep.
getting the defect.
Yep. You have perfect energy, defect structure energy, and the chemical potential. Yes.
Apart from defect formation energy, are you predicting something else about the defect, like maybe transition levels?
So we did not have electronic information aligned, right? We have energy information. So that's what this group of scientists did. They generated defects with different charges, okay, and then try to predict the defect formation energy. But yeah, there's some interest in predicting transition levels and stuff as well in this model. So one of my PhD students is working on that. Okay, so we talked about CNN models, we talked about GAN models, GNN models. Now we will move to large language models. Okay, so one of the first large language model was in 1967 called ELIZA. Then LSTM came, long short term memory model. Then there was other model from Stanford, Google Brain. 2017 was a really key age for transformer architecture, and when 2020 came, you know about this GPT-3 boom and everything. So, and again, there's been many other large language model for this. So we will try to use one of them in this work. There is only a snapshot of large language model in different field. So from 2018 to 2023, and you can see there are major companies such as Google. I think this is symbol of, I think it's, I don't forget. This from Meta, Microsoft. What is this one? I don't remember. Okay, and there Stanford, Cohere, and many other models. ChatGPT, OpenAI, of course, Google Bard, and so this field is really evolving very fast, faster than almost speed of light. So if there's anything faster than speed of light, probably the evolution of large language model. So especially from material science, this group of people led by Kevin Jablonka and Ben Blazek, they organized a hackathon, or almost hackathon. So because it is so popular, so they wanted to have a kind of a party in a way. That's what these hackathons are. So whatever you have something, you can have your own model and show it up like how it can be used for material science. So all this, and I'm also somewhere here, I don't know where, but I'm here somewhere. And so we also contributed to this very large effort of how many possible ways LLMs can be applied for material science. And there are like 14 examples they have shown. For example, text classification, like given this text, can you tell me it's an archive category of material science or archive category of bioscience? That's one of them. Converting into in a structured format, or extracting some chemical formula, or there's different applications like this for material science. So one of them is ChemNLP. Okay, there are many others. Just don't get me wrong. This is just again one of the project. So ChemNLP is a project which can be used similar to the image data set. It can be used for clustering and classification. Just classify based on text, or it can be used for named entity recognition, which is something similar to semantic segmentation. Remember we did the we did pixel-wise classification. Here is like word-wise classification. It can be used for summarization, right? It can be used for text generation. So one of the things we tried is we have the archive all the articles, and can we develop a model that given a title, it can write me abstract, right? Or given the abstract, it can write me title. So ideally what we want to have an agent. So few years ago there was an era of machine learning, big data science. Then came the era of deep learning. Then came the era of Gen AI, or inverse design. Now we are in the age of agentic AI, where they are developing a lot of agents. So like PhD agent or engineering agent. So what we want is an agent that I give a prompt, write me a paper on high entropy alloy, which can be submitted to and accepted in Nature, and this topic. So it will write the abstract, it will generate all the images, all the chart, and validate with experiment, DFT, whatever, and complete paper is ready. That is what the agentic AI should do. And they are probably doing this. There's in 2025, OpenAI claims that they will have a model that will be as good, if not worse, than a PhD student in whatever field. Yeah, it's coming soon. So get ready. So the first thing, similar to the image classification, we have text classification. Given this text, tell me it's positive, neutral, or negative, for example. Or it can be token classification or named entity recognition, where, for example, my name is Omar, or I live in Zurich. Here Omar is a person token, and Zurich is a I think geopositional something token, right? So you can have tokenization. It can be used for summarization, where you have input and just summarize, or you can have text generation. Once upon a time, actually my favorite thing, honestly, which I try for every model, is twinkle twinkle little blank, and whether I see whether it can complete it or not. So in the earlier days, that's how I tested a lot of LLMs. Just write this prompt, and some of them are really horrible, really horrible. They cannot complete this. So that's how it's very easy to throw them away. If they cannot do one twinkle twinkle little star, there's no point. It can do material science, in my opinion, right? So text generation, summarizations. Okay, so let's talk about. So these are some of the categories of tasks we can do with NLP. We are going at a very fast speed, I know, and please stay awake, because once you lose one of them, you'll be lost. Okay, so please stay attentive. So one of the applications of NLP is, one of the method is called TF-IDF. This is one of the most earliest methodology in natural language processing. What is TF-IDF? Suppose, TF is called term frequency. So suppose the oldest human fossil is a skull discovered in the cave of Eroria in Almonda. So you can count how many times the word D occurs, term frequency. That's what term frequency is. Now, you can have many documents, right? And if this D occurs many times, then probably it's not relevant across the domains, right? So that's called inverse document frequency. So you want to count the number of repeats for each document, and you want to count the number of repetition of that word across different documents, and have in a way that is kind of balanced. It should be there, but it's not too much. So that is called TF-IDF, term frequency, inverse document frequency. The TF is term I frequency in the document divided by total number of words in the document, and IDF is log 2 of total documents divided by documents with that term. Okay, and this was one of the earliest model. Yeah, as we were just explaining this, if a document has 100 words and the word coffee appears 5 times, the term frequency of this is 5 over 100. And if you have 1000 documents and the word coffee appears in 10 of them, then the inverse document frequency is log of 1000 over 10, which is 2. Now to get TF-IDF, you just multiply these two. So this another way. Remember, computers do not understand letters, words, they understand only numbers. So this is one way to convert text into numbers. So yeah, this is just the EDA part now, where we are trying to have in archive repository there are 1.8 or 1.5 million papers. Most of them are physics. So I was very curious, why only physicists have so many papers, while something like economics and statistics have so less papers? Do you guys have any guess why physics is so ahead of this? So same with the other EDAs, exploratory data analysis. We took all the articles of whatever a million or a few 100,000. We took the titles and abstract, put them together, and converted this into TF-IDF that we explained earlier. And that we truncate up to certain portion, like I think forget 1,000 or something like this. Certain numbers we truncated, and then we compress this into 2 dimension. And then this is how it looks like. You can see they start to make some sense. So all this purple one, semiconductor one, have some clusters. Same with the red one, which is quantum gas and so on. And same with the PubChem. COVID-19 seems to have its own island. You can see it doesn't overlap too much with others. So this can also be good for visualization. Also, when you're writing grant, this kind of images are very good. So the first thing is text classification. So given the title and abstract and title plus abstract, we want to classify what category of archive paper it is. That is a problem we are trying to solve. And we tried different type of model like support vector machine, Distilbert, random forest, linear regression, and graph neural network. We saw that we can, if you have title only, we can get up to 85% to 86%. If you have abstract, you can get up to 90%. And we can have title plus abstract, you can have more than 90%, 91%. And if you guys have Google Scholar account, right, you see how you have suggestions of papers. Something similar like model comes. Like whenever a new model is developed, it tries to classify it, whether it's belong to this person category or that person category, and just suggests it there. So, and also for PubChem, we get more than 97% accuracy. So 97 is pretty huge for text classification. So this shows that all the ResearchGate and Google Scholar. So next, tomorrow, if you want to make a company for have a Google Scholar kind of thing, you know what to do next, at least how to get started. You have a good business idea, right? So the next is called named entity recognition or token classification, where we want to classify each word. Okay, so for this we use a model called XLNet. I won't have time to discuss the architecture, but it's very similar to the idea of like CNN model or a unit kind of model. And here we want to classify each word, whether it's a process variable, it's a material behavior variable, whether it's beginning, whether it's you have beginning or intermediate word when you write a sentence, and then you have material, descriptor, I think chemical characterization, and some other categories. It's a part of the paper. So we found that for each, suppose you want to find out from all the papers how many chemical formulas have been ever mentioned, suppose. So this can be used for this, right? And we did something fun with this. So we took all that tokenized term, all the formula, and make a periodic table where if you click the element, it will show you the papers from archive. So if you are working on bismuth selenide, you go to this periodic table, click on bismuth and selenium, you get like, I don't know, 10,000 paper or I don't know, 50 papers. Click on the year, then you'll see what's new going on in that bismuth selenide. That's also a good way to search, right? This is an application of this. It's called ChemNLP. All right. One thing I did not show here because it was a little controversial. So what we did and we did not publish is who will work on a topic for the next paper based on the author correlation of author prediction. Whom we should work next for your collaboration? I can almost predict. So there are a lot of fun things. Okay, so now we will go into the inverse material design, which we talked about. This should be actually the earlier slide. Somehow I put it here. But the first paper, probably to my knowledge, of inverse material design is the paper by Alex Zanger, very well-known scientist in our community. He wrote a paper in Nature Chemistry called Inverse Design in Search of Materials with Target Functionalities. I want this property or this functionality, give me that structure. Okay. And so when we say inverse material design, we are going from property to structure instead of structure to property. Now this property can be scalar like band gap, superconducting transition temperature, or it can be spectra such as X-ray diffraction, yield spectra, XRF, I don't know, some other spectra, images such as STM, STM, or a combination of this to all of that. So it also allows to go beyond a funneling kind of approach where you have like a database, 100,000 materials, filter to 10,000, filter to 1,000, filter to 50, filter to 10 paper. People have done this for like, I have seen so many papers like this, I'm just bored to death. So anytime I see these kind of papers. But still, this is a good work. Still is good work. But what we want is direct prediction. Like I want this property, I don't have time to go all this database, just generate with the crystal structure or something. And that's where this kind of materials or this kind of methodology can be useful. And although it sounds again super fancy, right? Who doesn't want this? Everybody wants it. It's very challenging. Why? First, there is no physics model for this. There are physics models to given the atomic structure, give me the band gap, you can use DFT experiment, but there is absolutely no model, at least to my knowledge, given this band gap generated with the crystal structure. Does anybody know this? Any model that can do this? That's why we have to rely on AI models. Okay. there are certain methods like genetic algorithm. How are you doing with this time? We started 9:30, 10:30, so we still have 20 minutes. Genetic algorithm, Monte Carlo, cluster expansion, Bayesian optimizations. There are certain methods. To certain extent, they can generate new structures for a property, but they are very limited and very difficult to kind of model. And if you want to use AI model, what we need from the yesterday we are also saying this, we need a good database, we need a good model, and we need a benchmarking strategy. These three things are absolutely necessary. So we need to have a database. So because we have this for superconductors, we're going to use it for superconductor Jarvis DFT dataset. We have different type of models, GNN, graph neural network, and GPT, generative pre-trained transform models, and we'll see which one is better, and we'll have a benchmarking procedures. And we wrote 2 papers, inverse material design or superconductors and atom GPT. So the atom GPT idea is just a GPT for materials. So I think I mentioned about this yesterday as well. Attention is all you need. This is a very interesting paper, and if you have kids in your house, you know how much attention they need. So same with the computers and any architecture like this. What I mean by attention here is, let me try to simplify this a little bit. So suppose you have a bond, silicon, oxygen, nitrogen, phosphorus, hydrogen. The importance of this bond length to predict the energy will be different than importance of this bond. Does it make sense? Does it make sense? And then it also is composed to other atoms and is related to other atoms. So what is the importance or attention that is needed for this bond? If you can compute it in a nonlinear way, then you can model your system very accurately. So it's basically, attention here is basically the weights in a way. Huh? Weight matrix. Weight matrix, but also not just weight matrix, which is just linear. You need some non-linear contribution too from your neighbors and stuff. Not just that weight matrix, but that weight matrix is somehow correlated to other weight matrices too, right? And then that mechanism, they call it somehow attention here. Okay, and this is by Google, 2017 paper. It has got 140,000 citations.
What kind of
Papers. Yeah, I'll have to look into this, but they have like sine hyperbolic or some nonlinearity. Again, I'm super simplifying this. If you want to learn more this, read this paper. And in this paper, we have 2 things, encoder and decoder. So we talked about this, hi, how are you, I'm fine, tokenization. So this converting these words into a letter is called, converting the words into numbers is called tokenization, okay? And we can tokenize this, we can have a model that can encode this, we can have a model that decode this, and in this process understand the importance of each token and stuff in a non-linear way, and they found this model can somehow be intelligent, actually intelligence. So there's also a claim, this PhD level assistant I talked about, is not just AI, but this is called AGI, Artificial General Intelligence. So Microsoft wrote a paper which is like a book almost, like 400 pages. So what are the possible things these AGI models can do? Okay, and they have done really thorough work. If you search artificial general intelligence, not artificial intelligence, you can find what are the benchmarks, what are the tests you can do to find what is actually intelligence. It is, right? Not just extrapolation, but actually do meaningful analysis. Given a thought, just don't give me an answer, but actually think about this. And that model is called chain of thought, COT model. So again, the basic foundation of all this is this transformer architecture. And they have some terms I'll just introduce to you called query, key, and variable. And so basically you have I don't know how to describe it easily. So I mean, you have a word, and then you have a dictionary, like a Python dictionary thing, right? You have key and value, key and value, not variable, value, and from there they have some mechanism to find its importance, which is called attention. I don't know how to. And this is much better than a recurrent neural network, long short-term memory network, And so this transformer, before this transformer architecture, they were this model RN LSTM, but nowadays everybody has almost forgotten about this model, unfortunately. Everybody blindly using transformer for everything. However, I think the LSTM developers come with a new model which claim to be better than transformer 2. So there are some lot of controversy which one is better and whatnot. Anyway, so we are interested, we are material scientists. We want to know how can we apply this for material science. So one of the model we use, okay, one step back. So this transformer, there are many transformer models, maybe 100,000 transformer models based on how we can have weights and biases and how many layers and stuff. So this ecosystem is called Hugging Face. It's just like an emoji, right? So this Hugging Face is available at huggingface.co, and there are many models. One of the model that we found personally very relevant is called Mistral model. That again, there's a model from Facebook called Llama. There's a model from Google called Gemma. Microsoft has, I think, Phi. Several Chinese companies have this, and from a French company, this Mistral model is there. And I personally, at least for superconductor design task, found this Mistral model to be very promising for material design task. And we are actually in conversation with this company, like, can we do something better? Why are this working so much better? So we are in conversation with this company. So I asked them this question: why does it work so well for materials? Do you have any clue? So they have, of course, they are not going to tell you, they are a company, right? So first of thing, they don't tell you what are the new innovation they made, and second thing, they will not give you the data that they trained. They will give you the model, which is just weights and biases, but will never give you the data they were trained, which is if you consider entire internet data, there's trillions of tokens, and to train this trillion of tokens, do you know how much does it cost? Any guess? Who didn't attend my previous talk? How much does it cost to train a model for trillion tokens? Any guess? Wild guess? $1 million. It cost $1 million to train one model, which is really crazy, right? And it costs a lot of energy. So there's a huge controversy whether these are costing actually global climate effect and stuff. There are certain policies called carbon zero footprint or something like this. So most of these companies have this. So the idea is, if I understand correctly, suppose you use certain amount of energy, you have to plant certain amount of something to kind of make it neutral, or something like this. So most of these companies are trying to do this. But still, the amount of energy that being burned for training this model, and there's a huge competition, right? Everybody wants their model to be better, faster. Everybody has to try this million GPUs training. So we are not going to go there. We are material scientists, right? So for this one, and we don't have $1 million to train a model. So what we did is we took this model called Mistral from Hugging Face, which has 7 billion parameters. Do you know how many parameters or how many neurons are there in our brain? Any guess? Trillion? Okay, I heard trillion. Any guess? Quadrillion? Yeah, you can add as many zeros as you like. So apparently it's like 100 billions or 100 to 300 billions neurons in your brain right now. So out of that, I don't know how much is functioning right now. So you can see in your brain itself, you don't need so much neurons to work, right, for a particular task. And the energy, you can imagine how efficient our brain is. To train this model requires humongous amount of energy, and these companies are buying nuclear reactors now. They are not even the game is who can buy more nuclear reactors now, right? We don't even have a nuclear reactor for running this 100 billion parameter model, but we are still so efficient, right? So even we now making this decision, we are only certain part of our brain, like frontal lobe and so on. So same with these models. What we did is, of these 7 billion parameters, we varied only 100 million or 4 million parameters, something like this, and put everything fixed, and then fine tune that model only. So that is what Atom GPT is doing right now. Hopefully in future, if we have $1 million grant, we can try to train a model from scratch. Can anybody tell me what would be the advantage of training model from scratch? We can tailor this one too.
Control over the data set.
Exactly. So we never know what is the safety, because what if the output is, biasing some black people versus white people? There may be, so many things going to be there. We never know what is it trained on. So it's good to have a model from scratch, but because we don't have resources, we are relying on this model right now. But in future, that's the goal. So in Atom GPT, what we are trying to do, there are two types of models. One is called forward model and inverse model. In forward model, suppose we give a text description. Back to this forward model, we have a prompt like this is how a chemist will describe atomic structure. This is a magnesium boride crystal with hexagonal symmetry with this space group. This has a one short bond, one long bond, and so on. And this is my and some other things. This is how chemists will describe atomic structure. Chem NLP does this for you. Anytime you give a postcard file or zip file, it will write you this description. It has some tools for this automatically. So we generated this for all this 80,000 materials, right? Tokenize this, X, we get our X, and Y is the property. Y here in this case was superconductor transition temperature. So this is called forward model. And for this, we use the GPT-2 medium model, which is open access. GPT-3 and on is all, I think GPT 3.5 and on are all proprietary models, not available to anyone. So we use the open access model. This is forward model. For inverse model, we have a format called alpaca input. So in this one, you can see it's a dictionary. You have 3 keys in this dictionary. You have to have an instruction. For example, here is a description of a material or superconductor material. Next, you need input. The input is just the formula and the TC. That's all. That's all I'm giving as a prompt. And I'm asking it generate atomic structure description with lattice length, angles, coordinates, and atoms. So this generates this string, which has lattice parameters, lattice angles, atom types, XYZ coordinates of each atoms. And once you have this, you have the full atomic structure. So it's also text to text mapping, right? And that's what's happening for thousands of materials. And we trained this model, and we found that this can be used for generating new superconductors. And we compared this with existing models such as graph neural network model like Align, CGCNN, and Atom GPT, for some cases was beating them. It's very interesting to see. Graph took so many years, so much thinking, bond angles, atomic numbers, this, that, and this model just needs description and predict properties so accurately. So we found something is very interesting about this GPT models. Also for inverse model, the GPT models were much accurate in predicting new crystal structure. And we measure this using the bond distance error between the test set materials. Like suppose you have a test set of 100 materials. Suppose you have 100 materials, you have 90% training, 10% testing. So now for 10%, we know exactly atomic structure. Now Atom GPT or diffusion model generated the atomic structure. Now you can calculate all the atomic distance between this, or lattice parameters or angles, and see how much difference they are. So that's how we measure the efficiency of a inverse model. The performance, yes, is based on the test, but the model was trained on the training data set. Training is just a postcard file. So I'll probably have a demo as well. You have an Excel file. In this Excel file, and that is for all the machine learning model we have. You have an Excel file because we love Excel file. We have ID. Is this right? No, it's file name like postcard 1, postcard 2, and so on. This is just file name, and in this you have property like 5, 0, 1, 2, 5, whatever, 6, 9. These are the property of that material. That's all you need. And in the same folder, you have to have the actual postcard files. And once you give this, these models will automatically convert this into tokens and give you X, right, the input matrix, and Y from this one, right? Do a train test split, 90-10 split, train the model and test on this automatically. Yes, that's it. So for both forward and inverse model. So this output can also be multi-output. Like we have a model called Diffract GPT, and it just got accepted this week. I just asked Rohit to print me the copyright and stuff for this. So you can have multi-property too. So X-ray diffraction is kind of multi-property. You can map from this to that too. Again, I will not go too much on details of this because it's already 11 o'clock, but I want to point out these two things called LoRa and AMP. So the low rank adaptation is a way to have parameter efficient fine tuning. What it does is it captures the task specific knowledge and fine tune while keeping the majority of models original parameter fixed. If you remember from the linear algebra rank of a matrix. So what should be the rank of matrix when I fine tune this model with billions of parameter, how much chunk of matrix should I choose to fine tune and stuff. So those in a certain way, that's LoRa what it does. Second is automatic mixed precision. So we talked about we can convert floating numbers into integers in a very smart way to save memory, right? So when we fine tune this model, we use a combination of float and integers. So suppose we know some part of the model is more important, then we make it float, and the others we keep it as an integer. And when you calculate the loss function, then we only use high precision, because during loss calculation we cannot compromise, we have to have actual loss. So in this way we can have more efficient tuning of the model. And there is something called reinforcement learning, rotary position embedding. So instead of having a relation from one word to another word in a sequential way, it can be related back to itself too, and in a rotary position way. So using this principle, we will try to run some of these Colab notebooks for forward model, for inverse model, and so on. And this is one of the new superconductor we designed and validated with TC, superconducting transistor temperature 4 Kelvin, way away from room temperature, right? But it is a proof of concept that it can actually work. The second one of the next generation of Atom GPT is called Diffract GPT, and the idea is we can take a spectra like this, X-ray diffraction spectra, right, from 0 to 90 degree 2 theta angle, right? So suppose you have a spectra like this, or let me not call it spectra. People get, in experimental community, if you call it spectra, people get mad. You have to call this pattern or diffractogram. So suppose you have these peaks from 0 to 90. Now suppose we have, make it a bin from 0 to 1, 1 to 2, so on, up to 90 bin. Or to make it more precise, we can make it 180 to have 0.5 degree bin. Now we can count what is the intensity in that bin. Okay, so just make a histogram. Those are 180 numbers, 180 floating point numbers. Now suppose we typecast that floating point numbers. Actually do a round off to 3 digits, those numbers, typecast into string, and just add them as with spacing. So it becomes like 0, 1.5, 3.5, whatever that intensity, 6, 0. It's like this, 180. It's like a string. This is your x-axis, x data set. Y is your crystal structure, POSCAR file, CIF file. Does it make sense? So the idea is, if I give you XRD, can you predict me the POSCAR file? Although it looks very simple, although X-ray have been discovered for 100 years, I think 1895 or something like this, the X-rays were discovered. More than 100 years actually, very interesting. But still nowadays, there is no unique method that can map from XRD to crystal structure efficiently. There is none. There are some methods like Rite-Well refinement and so on, but they are very inefficient. There are a lot of things you have to do like manually and stuff. It's very time consuming. Wouldn't it be nice if you can make a model that just take XRD and give me the POSCAR file? So that's what this model motivation is. And before I publish this, NIST asked me to patent this idea. So this is under patent and also under publication. So once you generate, once you convert this diffractogram, yes, question.
The angle is not given as
Yes, angle is because x-axis is same for all the materials, right?
I versus 2 theta, that is what we generally correlate in normal also.
Right. But suppose the x-axis is same, 180. So suppose you have one material which looks like this, and another material which looks like this. Now, if we have a bin of 0 to 180 degrees and 0 to 180, and you have a peak number here 1, and here we have 0, 1, 1, 1, 0, 0, right? So they both are 180 in number. Does it make sense? They have the same number of peaks, same number of data, same number of data size, 180.
Okay. So essentially, wherever the value is there, that will correspond.
Yeah. So we don't need the x-axis anymore. Again, this is one way of doing this that we find. So once we convert this x-axis and postcard file or zip file into this, we can have a mapping. Now, sometimes chemist does not know what this chemistry is. We don't know what element is made of. That's one model. Sometimes they have some guess elements. Sometimes they know actual formula. These are three possibilities. So you can take this string, have this guess three types of structure, and meanwhile, just to have better guess, you can relax the structure using our unified force field model that we had, and that gives better candidates. That's one way of doing this. Another way, which is more common, is just match this with existing X-ray diffraction in your data set and give some candidate. So it's a complementary approach whenever you have new X-ray diffraction. Now, I want to point it out, there are several limitations for this model. First, if you have something like amorphous material, high entropy alloy material, where the XRD looks like a broad peak and stuff, it might not work very well because it was never trained for this. It was trained for only right now for the perfect materials in the Jarvis DFT. Perfect materials only, okay? But fun part, we also try this on defect materials. I'll show you. So again, before doing any machine learning, what do we do? EDA, right? Exploratory data analysis. So here we are doing this, what kind of crystal system we have. You can see most of them are cubic materials, but they are triclinic and hexagonal system as well. How the space group distribution is, so on, and how our theoretical data. So again, we did not, we could have got the X-ray diffraction pattern from ICDD dataset, International Crystallographic Diffraction Database or something like this, but it's licensed and stuff. We do have the license, but we do not have the license to do machine learning stuff on this. So what we did is, we took the Jarvis DFT dataset and we can compute X-ray diffraction readily, just you know the crystal structure. And we compare the experimental and theoretical. You can see they compare very nicely to each other, at least for these samples we tried. So the idea is if you can train the model on simulator, they can work well for experimental as well. And to my knowledge, XRD is the only method, at least powder X-ray diffraction, that can be easily calculated so easily just from the postcard file. I don't think there's any other experimental method, whether it's Raman or neutron scattering too, but Raman or ellipsometry, you still need to do some field calculation or DFT calculation and stuff. But XRD is probably the only method that doesn't require any subsequent. And that's why it's very powerful, because suppose you put some input experimental data, you generate crystal structure. Now you can do XRD of that and directly match how does it compare with an experimental input. Then you calculate the error. So we compared this three type of model where we have the diffract GPT with no formula, diffract GPT with element list, and diffract GPT with chemical formula. And we also have a model which can just predict the lattice constant, not the postcard file, but just the lattice constant using gradient boosting and convolutional neural network. So we have this feature X, and we are trying to predict A, B, C. That's it. So we found that this model with chemical formula gives most lowest error or most highly accurate model. And of course, this we don't have the atomic structure description for this conventional machine learning model, so we can't even calculate this metrics. So here's an example for silicon, which is a very popular material, of course, Lab6, which is a standard reference material, and hafnium carbide, which is, excuse me, a superconductor material. So, experiment. Is what? Is heavy? Yeah, I mean, XRD doing it like 5 minutes. If you have a powder sample, take 5-10 minutes. You can have a good scan, decent scan. I mean, if you want some more stuff, yeah, you can put in hours and stuff. But it's not that difficult. Suppose you have a new material. Yeah. So you have the input spectra, you know the chemical formula, silicon or something, and you put to the diffract GPT model, it generated the structure, and if you calculate the XRD of that structure, it will look like this. Now you can see this spectra had 6 peaks, this one had 7 peaks. I don't know, it's hard to see. It's just number of peaks, 1, 2, 3, 4, 5. Oh, the XRD pattern is very easy. Remember we talked about this? We have, so we have, suppose a Python array from -3 to +3, like -3, 1, 0, -3, 2, 0, all the possible Miller indexes, 1, 1, 0, 1, 1, 1. And from there you can calculate DHKL, right? And now you have all the possible DHKL, and then you have all the possible distances from actual interatomic distances from your atomic structure. Whichever matches, that will be your DHKL that you are observing experimentally. Also, if you want to calculate intensity, there are something called structure factors, which are well tabulated. So this is a small formula, like maybe there is a formula is there. It's like 10, 20 line of code. Given postcard, give me the XRD. So we calculated this, and there was like 7 peaks. Then you relax with a line force field, then we get 6 peaks back. It can be useful in that respect. Same with lab 6 and hafnium carbide. Now the fun part, oh, I don't have the picture here, but we did test for defects. So one of the way to test defect is, what if I have a silicon atom which has 2 atoms in the primitive cell and just slightly displace it. So if you slightly displace one of the atoms, the peaks will go up and down. I don't know if you have seen this simulation. So we actually manually displaced the atom and generated the crystal structure, and still we can found up to a certain extent this model can generate the crystal structure of the defect material. So it can be used hopefully in future for defective material as well. I was giving this talk at the department talk at material science, I think 2 days ago. A very nice gentleman, I forgot his name unfortunately, he gave me suggestion, you should have this model tested for mixture of powders. So suppose you have hafnium carbide, hafnium nitride, mix them together, can you identify which material is what? So that will be the next thing to do. So whoever that person is, thanks to them. That's the thing, when you talk to audience, you get new ideas. Okay, so last, I promise this is the last thing on reproducibility, okay? Absolute last. So there is a paper in Nature called 1500 Scientists Lift the Lid on Reproducibility. So reproducibility is basically, if I have a number in your paper, how, if I want to reproduce that number, how accurately, how efficiently I can reproduce this. So people who attended my talk the other day, that's fine, don't answer, but people who did not, can you guess how many papers, how many percentage of papers are reproducible in literature? Pretty less. How much? 0. Pessimist guy. Sorry. 5%? Any guess? 5%? 20%? Same. Okay. You are close enough. That's what I'm saying. It's 0.5% for some case, and for some maximum is 30%. Of course, it depends on the field, right? So for some of the field is 0.5%. This is crazy. 99.5% papers are non-reproducible. So I believe if you have black magic versus science, the difference between this is reproducibility, right? It seems like if you keep doing this kind of process where things are not reproducible, there is no point actually doing science. So we have to step back and work on reproducibility a little bit more enthusiastically or more smartly, I don't know. So we come up with this idea called Jarvis Leaderboard, which was a platform for benchmarking different modality like AI, electronic structure, force field, quantum computation, experiment. We have currently like 1,000 benchmark like this and several contributions. We'll talk about this. So idea is anytime you have a paper published, you will put your data in like Figshare or something like this, put your code in GitHub, and if you want to have reproducibility, you add your reproducibility thing here. And I'll show you what are the things that is minimally needed for reproducibility. And it's very easy to, relatively easy to work with, and it can support experiments as well. And in terms of experiments, what I mean by reproducibility is round robin experiment, which is you take a sample, measure different labs and calculate the error or something, right? and it's fairly easy to use. Now, why benchmarking is so important in our age? Because almost any company you look at, they are having their own benchmarks for their own domain, right? So, for example, we saw a news like ChatGPT beat a medical doctor benchmark, or a lawyer. You can replace a lawyer or something like this. But can you are reading this in a newspaper, can you actually reproduce that? How many of us can reproduce that? We are being kind of being believed, making make believe in a way we cannot even reproduce this. So we should not, science should not be like this. That's what my point is. So we were in 1900s, not me, some other. It was like dealing with example data and stuff, right? Now there was data sets development from MNIST and so on in 1900. In 2000 there was multimodal data like text, image and so on. 2010 it was big data. Maybe you were kids back then. So some of you at least. Big data, and now it's all about benchmarks. Every company is coming with, I have a model that can beat this model on this benchmark, I am the best, right? But how reproducibly can you verify this? Very minimal. So I'll show you what kind of things we can do to enhance reproducibility. And in this paper called Jarvis Leaderboard, we have about 40 co-authors from almost all national labs in the United States, all the major, not major, but most of the major universities. We have about 30 contributors or 40 contributors who have kind of given their data in a way to enhance reproducibility. And the idea is we can submit this platform in different national labs, and over the years see how things are reproducible or not, the entire thing, right? And keep a track of everything. And this requires a lot of funding and this, so we got funded for this. This is a beautiful idea. So we are working on this topic so we have electronic structure, AI, force field, quantum computation experiments, and we have DFT, quantum Monte Carlo, tight banding, and many other methods, both theoretical and experimental methods like this. And there, as I said, there are different national labs, different countries like Germany, Canada, of course US, all of them are contributing. Hopefully we can have some contribution from India as well. So we have currently 9 million data points, and most of them have notebooks. The notebooks we are dealing in the tutorial, that's also part of the reproducibility component, and several benchmarks. We have category, but we also have subcategory. So these are all flexible. We just made it up, but you can also make other ones if you like. Like there can be property from AI, like formation energy is a scalar property, single property, or it can be class, metal versus insulator, or it can be machine learning force field, text classification, we talked about that, token classification, text summarization, text generation, atom generation, like atom GPT, image classification, spectra, eigensolver, and you can have multiple category like this. So just to let you know what this is made of, if you go to the Jarvis Leaderboard, there are only two main folders. One is called contribution and one is called benchmarks. Okay, for anything to be called a benchmark, it must have a peer-reviewed DOI article with this, else we will not call it a benchmark. This is a minimum guideline. So for example, there was a claim of superconductivity, right, few years ago, 2 years ago, maybe 1 year ago, room temperature superconductor from South Korea, but it was not peer-reviewed, so we will not put it here, if it makes sense. So there's a difference between database and benchmark. Database, you can have many repeats things, like magnetic moment of 1 million materials, same formula, same everything, repeats it. But benchmark are kind of holistic data. All the ground truth data, all the standard data will be stored there. It will be small, but very useful. So anytime you want to make new database, you'll benchmark against this and then follow on from there, right? So that's different. Does it make a difference? The difference between the benchmark and a database, is it clear? So for a benchmark, we have this DOI based article, and for what is the contribution? So the contribution is the method or experiment that you are trying to do. So for electronic structure like DFT, you'll predict like bulk modulus and compare with experimental bulk modulus, right? So the benchmark is experiment and DFT is your method. Same for artificial intelligence is a test data set. Remember we did 90-10-10 split or 80-10-10 split. The test data set is the benchmark reference point. The force field is the electronic structure. For quantum computation is analytical results. And for experiments is other peer-reviewed article experiments. Okay. So when we have, as I said, there are two folders. In these two folders, we have these categories, AI, electronic structure, and so on. And then we have subcategories like image classification and so on. and in this we store JSON file, and in the JSON file is a format where we store the identifier of that material. So we are not actually storing each postcard file or something. We have an ID of that material and then corresponding property, and whether it's a part of training or test, so that the training and test, for example, for AI is well defined. Now, if you have a new model, like a classification model, you will submit this CSV file. We will have the ID and the prediction, where the ID will be the correspondingly, you can see 1408 here, 1408 here. So for your model, what is the prediction, and so on. And then when you upload this, the GitHub action will automatically merge this based on identifier, calculate the metrics, populate the website, and send me an email or my team an email that this is ready, and I'll see whether it makes sense, approve it, and then it becomes the part of the website of NIST forever. So it's totally automated. And for each file, we have metadata.json file, which is basically who did it, what's the email of that person who contributed, those kind of things. What is software it was used, what hardware it was used, what experimental tool was used, what kind of condition of environment was used, that kind of metadata. Run.sh is a shell script especially for theoretical simulation, that if I submit this, it will first install the software, get the input file, run all the calculation, and at the end generate the CSV file, so that I can have complete reproducibility. Okay, so these are the components, and it looks like this. This is an example of AI formation energy model. So you can see there are at least 10-20 models, and for this one has the highest error, this has the lowest error, and this is how the run.sh kind of should look like, and so on. So I think that's it. We made it through. So if you still have some brain left, we'll try to go over the hands-on session and get it more real. So my recommendation would be, once we did this exercise and did the hands-on session, a few months from now, try to watch this video. This video will be available, and watch it again and try to do this again. Then it will go deep in your blood somewhere, in your subconscious mind, unconscious mind, or whatever they call it. Then you will become, some new ideas will come up and write papers and stuff. Okay, see you again.